Question number 3. One end of a light elastic string of natural length 0.4 meters and modulus of elasticity 20 newtons is attached to a fixed point A on a smooth inclined plane at 30 degrees to the horizontal. The other end of the string is attached to a particle P of mass 0.5 kg which rests in equilibrium on the plane. Calculate the extension in the string. Before starting the question, let's draw the diagram. We have a plane inclined at 30 degrees and we have a particle P attached to a point A with a light elastic string of natural length 0.4 meters. Let's assume that this is the natural length and the extension, let it be x meters. As we know, there is tension acting in the string in this direction away from the particle. Let's write that as T newtons, tension T newtons. There's the weight mg acting downwards. This force has two components. One is the horizontal component and the other is the vertical component. If you project it downwards, this line, you get a 90 degrees angle, and this is going to be 60 because 90 plus 30, 180 minus that is 60. Resolving this force in the horizontal direction, we get mg cos 60, and in the vertical direction we get mg sin 60. After taking the vertical and horizontal components of the weight, since the particle is in equilibrium, which means it's at rest, both the forces should be equal, the tension and mg cos 60. And it is given in the question that there is no friction acting on the plane, so you don't need to worry about the frictional force. Let's equate tension and mg cos 60, which is the horizontal component of the weight along the plane. Tension is given by lambda upon L into x, where lambda is the modulus of elasticity of the string and L is the natural length of the string and x is the extension in the string. Mass, we know it is 0.5 kg, so the particle P times gravity is 10 and cos 60. Right, substituting the values given in the question, lambda is 20 Newton, L is 0.4 Newton. Placing that in this equation, we should be getting x is 0.5 into 10 into cos 60 into 0.4 divided by 20. You should be left with x as 0.05 meter. Moving on with the second part, it says P is now projected down the plane from the equilibrium position with the speed of 5 meters per second. The extension of the string is E meters when the speed of the particle is 2 meters per second for the first time. Find E. Let's set up the diagram. .30 degrees And initially we have a particle here. Now this particle is projected down the plane with a speed of 5 meters per second. So the motion of this particle is going to be like somewhere here. Yeah. It's going to come there with a speed of 2 meters per second. Let's assume that the speed of the particle at that point is 2 meters per second. It's projected with speed of 5 meters per second. In order to find the extension in the string, which is from the natural length 0.4 meters, we are going to consider the energies of this particle at both points. So before finding the energies, let's find the height, the change in height when the particle is moved from the equilibrium position to this position. Let that be h. Okay. As we know, the extension in the string when the particle is in equilibrium position is 0.05 meters. That's the extension in the string in equilibrium position. And this whole extension is E. So this is going to be E minus 0.05. And h is given by this angle will be 30. Sine 30 into E minus 0.05. This is the height. Now writing the energies, total energy at equilibrium position, we have kinetic energy plus elastic potential energy plus gravitational potential energy. I'm going to take this as the zero level, so the gravitational potential energy will be zero because I'm going to consider this as the zero level. Kinetic energy is half mv square plus elastic potential energy is half lambda by L into extension square plus GPE, that is mgh. Half mv square, so the speed of the particle initially is 5 meters per second and mass of the particle is 0.5. So substituting that, you should be getting half into 0.5 into 5 square plus half into 20 upon 0.4 into 0.05 square plus 0, as height, change in height is 0 at the initial point. Solving this, you should be getting it as 6.3125 joules. This is the energy at the initial point. Okay, so now we're going to write the energies of the particle at this point. At that point, we have kinetic energy plus elastic potential energy plus gravitational potential energy. Kinetic energy at this point is half mv square, where the speed is 2 meters per second. I'm going to substitute that later. Elastic potential energy is half lambda by L into extension square. The extension is E. I'm going to substitute that later. Gravitational potential energy is mgh. Okay, so substituting the values, we will be getting half 0.5 into 2 square plus half into 20 upon 0.4 into E square plus 0.5 into 10 into the height, which is minus sine 30 into E minus 0.05. Because as the change in height, it's coming downwards from the zero level. So that's why we take a minus sign. Simplifying that, you should be getting 1 plus 25 E square plus minus 5 by 2 E plus 0.125. We're going to note this down, which will be used for further calculations. Using the law of conservation of energy, energy at this point is equal to energy at this point. And we have found that the energy at this point is 6.3125, and that is equal to energy at this point, which is 1 plus 25 E square minus 5 by 2 E plus 0.125. Simplifying all of that, you should be getting a quadratic equation: 25 E square minus 2.5 E minus 5.1875 equal to 0. You should be getting this quadratic equation from this. Solving for E, you should be getting E as 0.508. I'm going to leave the solving part to you guys.